Hi guys, in the last lecture we studied about the steady state stability. So we first saw what is meant by steady state stability. It meant that the system must remain in synchronism with the externally connected network upon occurrence of a small disturbance. Then after that we determined the criteria for the steady state stability, in which we saw dp by d delta must be greater than 0 for the system to be stable, and if dp by d delta is less than 0, system will be unstable, and if dp by d delta is equal to 0, system is marginally stable. Okay, and then we determined the frequency of oscillation. Omega was under root del pe by del delta at delta is equal to delta naught divided by m, or it can also be written as under root del pe by del delta at delta is equal to delta naught in pu pi f by h. Then we studied about SVC, that is static var compensator. When we connected it at the midpoint of the line, then power became 2 times P max into sine delta by 2. So maximum power capability was increased, due to which steady state stability improved. So these all concepts we covered in last lecture. In this lecture we will see a few problems based on steady state stability and then move on to the case of transient stability. So let us see first few problems. In our first problem it is saying a synchronous generator of reactance 1.2 pu. So X is given to me 1.2 pu is connected to infinite bus bar, that is mod 1 is equal to 1 pu through a transmission line of reactance. So this will be, let us say, Xg. Transmission line reactance is 0.6 pu. Inertia constant H is given as 4 second. Resistance and machine damping is negligible. I told you why we neglect the resistance and machine damping, because we neglect any such term which will tend to make the system stable. So resistance will also dissipate the energy of oscillation. Same is the case with machine damping. Machine damping refers to the damper bars or damper winding. Then frequency is given to me 50 Hertz. It is saying that system is loaded to be 50% of maximum limit. We need to find frequency of oscillation. Now one thing we know is that P is equal to P max sine delta. Now it is given to me 0.5 P max. So from here I can calculate delta. It will be 30 degree. Now since we know delta, we know the frequency of oscillation omega. Omega we wrote it as del P by del delta into pi f upon h. So first we have to calculate del P by del delta. Since P is equal to P max sine delta, del P by del delta would be P max cos delta. Now I know the value of delta is 30 degree, but I do not know the value of P max. So first let us calculate P max. If we wish to calculate P max is actually mod E mod V by X. Now how is my system? System is like this. Here we are given mod V is equal to 1 pu. Mod E, this reactance is given to me 1.2 pu. This is 0.6 pu. Now since both these systems are connected in series, what will be the equivalent reactance? 1.8 pu. So what will be P max? It will be 1.2 into 1 upon 1.8, that is 2 by 3. Now let us determine the frequency of oscillation. It will be under root 2 by 3 cos 30 into pi into 50 by h, that is 4. So this frequency will come out to be, so this will be omega actually, or let us directly write frequency is equal to 1 by 2 pi times this. So this will come out to be 0.758 Hertz. Okay. So remember, the formula that we derived was for omega. If it is asking frequency, you have to divide omega upon 2 pi. Okay. So do not leave the last step, because otherwise all your effort will be wasted. You may be applying the right formula, but do check the units in which it is asking the frequency. If frequency is asked in radian per second, you will find omega. In hertz, you have to find omega upon 2 pi. Let us move on to the next problem. In our next problem, it is saying an alternator is connected to infinite bus. Now, since figure is not shown, let me draw it for you. An alternator is connected to infinite bus. Now, this is my infinite bus. So, the alternator delivers power of 1 pu. Okay. Then, it delivers a current of 1 pu, it is given. Okay, power factor is given to me 0.8. Voltage is given as 1 pu. Now reactance XD is given as 1.2 pu. We need to first find the active power output. Now there are two types or two ways to find the active power output. P can be written as mod E mod V by X sine delta. But for that we need delta and excitation. Here we have current, power factor and voltage, but we do not have delta or the excitation. That means this formula cannot be directly applied. But how to apply? If you want to apply this formula, you will write E is equal to V plus J IA XD. Then it will be 1 angle 0 J into IA. IA is 1 angle minus 36.86. XD will be 1.2. So this way you can calculate E. It will be equal to mod E angle delta. So you will get mod E as well as delta. But this will involve phasor calculation. So to simplify the effort, the other way to find power, it is also equal to Vi cos phi. Now V is given to me 1, I is given to me 1, cos phi is 0.8. So directly power comes out to be 0.8 pu. So that is why you do not need to cram up the formulas, rather you need to see which formula suits the problem best, because to find the same quantity there may be multiple expressions. Now it is asking the steady state power limit. The steady state power limit will be P max, that is equal to mod E mod V by XD. But for that we need mod E. Now to determine E, we will apply the phasor equation, that is 1 angle 0 plus J 1 angle minus 36.86. Why minus 36.86? Power factor is 0.8 lagging. So this will come out to be 1.97 angle 29.17 degree pu. What will be P max? 1.97 into 1 divided by 1.2. So how much will this value come out to be? 1.64 pu. Now this is my steady state power limit or active power limit. In the next part it is asking keeping the active power output fixed, that is P is constant. Okay. If excitation is reduced, we need to find critical excitation corresponding to operation at stability limit. Now if we go on reducing the excitation, then P max will go on reducing. Operation at stability limit means P will be equal to P max. Okay. So if P is kept fixed and we reduce E, P max will go on reducing. And if it becomes equal to P, that will be the critical limit. Because if P max goes below P, then system will become unstable. Because active power output should never be greater than P max, otherwise system will lose synchronism. So critical case will be P is equal to P max is equal to 0.8. So mod E, mod V is 1, XD is 1.2. So it will imply that excitation will be equal to 0.96 pu. So if you reduce the excitation to this value, then operation will be at the stability limit. That is, you will be operating at a power angle of 90 degrees. That is delta equal to 90 degree. Okay. So in steady state stability analysis, two things you have to remember. One is the frequency of oscillation, and the second thing that you have to remember is the maximum power output of a machine. Okay, that is mod E mod V by X. Now let us move on to the transient stability. So first of all, what is meant by transient stability? It means that the system remains in synchronism with, let us say, infinite bus or the power grid even after experiencing a large disturbance. So this definition differs slightly from your steady state definition, because there we were considering the small disturbance. The only thing that you have to change is replace small disturbance by a large disturbance, and if still the system remains in synchronism, it will be said to be transient stability. Now large disturbance may be due to short circuit fault, because whenever the short circuit will occur, the voltage will go to 0, due to which the power will also be reduced to 0. Now if suddenly the power goes to 0, then there is a large disturbance, because suppose the generator was earlier delivering 100 megawatt. Now suddenly power becomes 0. So it starts delivering 0 megawatt. So there is a large change in the power output that is equal to 100 megawatt. Hence this will lead to transient stability problem. Next reason is due to contingencies. Now actually a contingency study is nothing but it is a kind of backup plan. So what happens, suppose if some apparatus gets damaged, let us say a transformer gets damaged, then whether or not my system will remain stable, because if somehow some apparatus also gets damaged, then system must continue to be operative. Okay, so that is called as contingency study. In this, what we will do is we will remove some apparatus. Now suppose there are two transmission lines, equivalent reactance is x by 2, and these are circuit breaker. If we open circuit this, then the reactance will be x. Now since reactance suddenly changes, Pmax, which is inversely proportional to reactance, xt means transfer reactance, so Pmax will also suddenly change, which will lead to a large disturbance. That is called as your contingency study. That means whenever you remove some apparatus from a power system, the operation of the power system will change, because the power capability of the system will change. And still if the system remains in synchronism, it is also called as transient stability. Okay. So transient stability is done by introducing a large disturbance which is due to short circuit or contingency. Then the question that comes to mind is, why transient analysis? The purpose of steady state analysis was to determine the maximum power output. Why? Because that is the maximum loading of the system. You cannot put the load beyond the maximum value. If you do so, system will lose synchronism. So you kind of get an upper bound as to how much power you can extract from the system, because if you extract more than that, then system will be unstable. Then what shall be the purpose of transient stability analysis? The thing is, when we will study transient stability cases, we will discover a fact that if the fault is not cleared beyond below or before a certain time, called as critical clearing time. If fault is not cleared before this time, then system will become unstable. Okay, that means the operating time of circuit breaker must always be less than critical clearing time. Okay, I will tell you how it will go to unstable region if fault is not cleared before that. Okay, so this is one of the reasons, this is one of the design specifications of a circuit breaker. Whenever we are choosing a circuit breaker, we must have in mind what is the critical clearing time of my system. So buy a circuit breaker which has a higher speed than the critical clearing time, or whose operating time is less than the critical time. Now what are the assumptions behind transient analysis? First is that generator will again be modeled as a constant excitation in series with a subtransient reactance. Okay. So in any case, whenever a fault will occur, the excitation will be assumed to be constant, because in case of synchronous generator, the excitation comes from a DC source or a DC voltage source. So DC voltage source will be unaffected in case of a fault. Next is we will neglect saturation and saliency. Now why we are neglecting saturation? Because if we neglect saturation, then EF is proportional to IF. So that means I can easily control the excitation of the machine, and that is very important for the case of transient stability analysis. Otherwise, what will happen if the machine saturates? Then EMF will not be controlled by the DC excitation. But if you have to keep EMF constant, then DC excitation should be directly proportional to EMF. So that if DC excitation is kept constant, the EMF does not change. But if the machine saturates, then EMF will remain constant no matter what is the DC excitation. Why neglect saliency? Now in case of salient pole machine, what is the power expression? EF Vt by Xd sin delta plus Vt square by 2 1 by xq minus 1 by xd sin 2 delta. So if we plot the curve, the first power is your electromagnetic power, the second term is your reluctance power. So this will be my first power, this will be second. So overall power will be like this. So Pmax is higher. In case of cylindrical rotor, this will be the Pmax, but in case of salient, this will be the Pmax. So Pmax in salient pole is greater than Pmax in cylindrical. And we know as Pmax increases, the stability improves. So we have to neglect the saliency because we are doing the worst case analysis. So in general, salient pole alternators are more stable as compared to your cylindrical alternators. Okay, so whatever assumptions we are making to ensure that we are doing the worst case analysis, and there is no phenomena occurring in the system which will tend to make the system stable. So next assumption is damping is neglected. Because if you consider damping, it will damp out the rotor angle oscillations, which will make the system stable. Okay, so damping is neglected. That is, I am neglecting the damper bars. Next, resistance will also be neglected similarly, because resistance will also dissipate the energy of oscillation and will damp out the oscillation. Similarly, shunt elements like shunt admittance of the transmission line is also neglected. So transmission line is actually modeled as just a series impedance, that is Z, which is equal to Jx, because resistance is neglected. Next is frequency is assumed to be constant. Okay, this will enable us to analyze the system in a easier manner. Now, two most important assumptions are, in case of an alternator, there are two type of control system. One is your speed governor. What is a speed governor? Which will control the speed of the machine to control the frequency. It will control the speed of prime mover. So it is deactivated. Why? Because it will tend to make the speed constant. If it tends to make the speed constant, then we will not be able to study the oscillations in speed. Okay, it will keep the speed more or less constant, but we want that the speed should oscillate, then only we can observe the rotor angle oscillation. So it is deactivated. Similarly, AVR, that is automatic voltage regulator, what happens if Vt decreases? What it will do is it will increase IF so that EMF increases, so that Vt also increases. Okay, So in this manner it will try to keep terminal voltage constant. So it can increase excitation. Now suppose in case of a fault, electrical power output reduces. It may not become 0, but it may be some lesser value, because most of the current will flow into the short circuit. Less current will be passed to load. So the opposition should be that P must increase. This will improve stability. Now P is actually P max sine delta. To increase P, you can increase P max, and P max can be increased by increasing excitation. Okay. So if you increase excitation, maximum power output will increase, which will cause the system to become more stable. That is why we have to neglect the action of AVR. So here we have neglected every factor that might contribute to the system stability. So these are the certain assumptions on which our transient stability analysis is based. Now whenever we are talking about transient stability analysis, we have to consider what is the power transfer between the generator and the infinite bus. This is my generator, this is infinite bus bar. So here we take three cases. First one is your before fault occurrence. Now what happens, as I told you, mod E is treated as constant. Just now we took an assumption. Mod V is constant because it is a part of infinite bus bar. Now power actually depends on P max sine delta. So if you have to keep P max as variable, E and V are constant, we will consider the effect on transfer reactance. Okay, that means in the event of a fault, what will change is the transfer reactance between the sending end and the load end, or between the generator and the load. So that is why whenever we are considering the three cases, before the fault, during the fault and after the fault, every time we will see a different reactance or a different transfer reactance. Okay. So what we are assuming is whenever there is an abnormal condition in the circuit or there is a fault, how it will affect the system? It will change the transfer reactance between the source and the load. So we are considering the effect of fault on the transfer reactance. So now before the fault, transfer reactance will be assumed to be X1. Okay. Here this is a power system network which may consist of resistances, inductances, something like that. And since we are neglecting resistances, it will mostly consist of inductances. There may be two parallel lines, there may be three parallel lines, there may be bundled conductor. Any sort of a power system network is possible. And this we have shown that a fault occurs in the power system. Now before the fault, since transfer reactance is assumed to be X1, what will be P max 1? 1 indicates before the fault. Mod E mod V by X1, and power will be P max 1 sine delta. Similarly, we will define the next case, that is during the fault. During fault means when the fault has occurred and still we haven't opened the circuit breaker to clear the fault. That is, fault is still ongoing in the system. We will consider the reactance as X2. So P max 2 will be mod E mod V by X2. PE will be equal to P max 2 sine delta. Okay. 2 here represent that the system is during the fault. Similarly, after fault, that is after the circuit breaker has been opened and the faulty part is removed from the system. Since you might have removed some part from the system, the reactance of the system will change. So here we will consider the reactance as X3. So what will be P max 3? It will be mod E mod V by X3, and power will be P max 3 sine delta. Okay. So these are the three cases which we will consider when we will be studying about the transient stability analysis: before the fault, during the fault, and after the fault. Now here, since we have defined three maximum power, so before the fault, system would be operating in steady state. In steady state, I told you that Pm is equal to P max 1 sine delta. So delta naught will be sine inverse P max 1. Similarly, after the fault has been cleared, system must settle down to a new steady state. Whatever will be the steady state now, then Pm will be equal to P is equal to P max sine delta 1, let us say. So delta 1 will be sine inverse Pm by P max 3. Okay, because P max 3 is the maximum power after the fault. So this will be P max 3. So that is, the system is in steady state before and after the fault is cleared. Before the fault occurs and after the fault is cleared, system goes to steady state. And the condition that we were studying during the fault, that is actually transient condition. So that is why P max 1 and P max 3 represent steady state stability limit, triple SL, that is steady state stability limit. That is, for maintaining the steady state stability of a system, power must not exceed P max under the steady state, because before the fault occurrence and after fault is cleared, system is in steady state. Similarly, P max 2, that is your transient state, is called as transient stability limit. Okay, so what is transient stability limit? It is actually maximum power transferable during the fault. This is the maximum power that you can transfer from source to load when the fault has occurred. And if you are considering that the entire current goes into the fault, no current goes from source to load, so P max 2 is 0. Okay, if I fault is equal to I total, that means load current is 0. So P max 2 will be reduced to 0 because no power will be transferred from source to the load. Entire power will be going into the fault. Okay, so remember the terms steady state stability limit and transient stability limit. And remember one fact, that you can exceed transient stability limit, that is, mechanical input or shaft input can be greater than P max 2, but it can never be greater than P max 1 or P max 3. Because we will judge steady state stability only under steady state. During transient, it does not matter whether you are drawing more power than the maximum or less than the maximum, because system is not under steady state. So steady state stability and transient are two different phenomena. Steady state stability will only be studied when the system is under steady state. There you have to ensure that the shaft input of the machine must be less than P max. But during transient state, when the system is oscillating, you can exceed P max, but that is only for a shorter duration. You cannot settle down to a value greater than P max. You can only temporarily exceed that. That is why TSL can be exceeded but not triple SL. Now, the method to determine the transient stability is by solving the swing equation. But every time solving a differential equation is not that easy. So we need a simpler criteria to simplify the analysis of transient stability. Such a criteria is called as equal area criteria. Now here what we do is, this is a special case of swing equation. The basics is still swing equation, but we are finding a special solution for simplifying the analysis. But limitation is only single or two machine. Why two machine? Because we studied whenever there are two machines in a system, they can be represented by an equivalent single machine system. That is why at the most you can have two machines or one machine, but not more than that. If multi machines are there, then you have to use swing equation. And actually swing equation cannot be directly solved. Why? swing equation is actually h by pi f d square delta by dt square is equal to Pm minus Pmax sine delta. Okay, P is actually Pmax sine delta. So here delta is there and here delta is in terms of sine delta. So here we actually require numerical solution, and that is beyond the scope of GATE examination. So we will not see how to solve a swing equation numerically. We will only concentrate our attention on the equal area criteria. So now let us see what is equal area criteria. The swing equation in actual values is given by md square delta by dt square is equal to Pm minus P, which I told you is also called as accelerating power. Okay. Now to simplify this equation, what we have to do is, this is Pa, or we can say that d square delta by dt square is Pa by m. Now multiply both sides by 2d delta by dt. What I am doing is I am converting it into a differential. Okay, now this will be d by dt of d delta by dt whole square, and this will be 2Pa by m d delta by dt. Now if you integrate both sides with respect to with respect to t, d delta by dt square into dt should be equal to integral 2Pa by m d delta by dt into dt. Now if you cancel out dt, though it cannot be cancelled directly, it will look much more simpler. Since m is constant, this will be Pa d delta. Now if we integrate both sides, what we will get is d delta by dt square will be equal to 2 by m Pa d delta. Then d delta by dt will be under root 2 by m integral Pa d delta. Now for stability, the system should have an oscillatory response in which it finally settles down to steady state. Now if you see, if you are settling down to a steady state, or if you are showing the oscillatory behavior, then your initial state must be same as final. If system is oscillating, initial and the final state must be same, and if initial and final state must be same, then d delta, that is change in delta, must be 0, or we can say d delta by dt is 0. And from previous expression I can say that due to which Pa d delta is 0, that is area under accelerating curve, accelerating area under accelerating power must be 0. But if you see d delta by dt is non-zero, then delta will go on increasing. It will not show the oscillatory behavior, but if it shows oscillatory behavior, then d delta by dt is 0. Okay, and in case of your transient stability or equal area criteria, we only analyze first swing stability, because in case of first swing we obtain maximum overshoot. As we have studied in control system, first overshoot is maximum, and if system is stable under maximum overshoot, then other overshoots will be less than this. System will definitely be stable. So we have to just take care of the first swing. First swing means when delta moves from the minimum value to the maximum value. Okay, from the first minima to the first maxima, that is called as first swing. So equal area criteria is the first swing stability criteria. Okay, so the condition becomes an integral Pa d delta must be 0, that is area under the area under accelerating power curve must be 0. Okay. So let us summarize what we have covered in this lecture. We first saw what is meant by transient stability and what is the purpose. The purpose is to design the speed of circuit breaker. Then we saw what are the assumptions behind transient stability, in which I told you we have to neglect the effect of AVR and the speed governor or the machine damping and resistance to assume or to ensure that we are doing worst case analysis. Then we saw, after looking at the assumptions, what is the power transfer. I told you whenever there is a fault in a system, the transfer reactance between sending and the receiving end will change. And last we saw equal area criteria, which was a special case of swing equation for single machine or two machine system to determine the transient stability. Okay. So this is how transient stability analysis is done. In the next lecture, we will look at some cases in which we will introduce abnormal conditions into the system and see how the system will behave. That we will cover in the next lecture.